Okay, well, thank you very much for inviting me here to give this presentation. So I work at ECMWF. I'm in charge of the Dutch people too. So I'm in charge of the reanalysis team, so here I'm a co-author, but also more people than we submitted the abstracts for. Because the reanalysis touches many aspects, and there's a lot of people inside the team, outside the team, within the research department as a whole, within ECMWF as a whole, with our contractors and many collaborators. Okay, so to go to the next one, is that? Okay, yeah, good. Good. So overview for my presentation. I will give an overview where we are with ERA5, then where it fits into other reanalysis activities that we've done in the past and which we will do in the future, then towards ERA6. And although it's not in my title, I also want to have a little look beyond ERA6, and I will finish with some final remarks. Okay, so ERA5 is a global reanalysis, 31-kilometer resolution, hourly from 1940 to 5 times behind real time, and we run that operationally. Every day, one new day is added. And you have to remember that ERA5 was built on the shoulders of other ECMWF reanalysis. So if you look at this plot here, which shows how many days you have a skillful forecast from ERA5 analysis based on some criterion, you see that ERA5 is on top of the other reanalysis from ERA15, ERA40, ERA interim. But you also see that ERA5 is the longest of all of them. We have nearly 85 years now. And so we're building on the shoulders of other ECMWF reanalysis, and each ECMWF reanalysis is built on an IFS cycle, which is, again, stands on the shoulders of literally thousands of researchers at ECMWF that have been working at ECMWF for the last almost 50 years. So it's very popular. We have over 170,000 users, and we provide petabytes of climate data. So we have a lot of different users that will fill a conference as its own to go through all the applications that exist for reanalysis, and it's still growing. So this gives an example from accurate timely climate monitoring, where you have this near real-time product is required, which we do particularly also in-house at ECMWF, particularly to studying of historic extreme cases. This is an extreme storm in 1941 over the Iberian Peninsula. And this is something we never thought about would happen when we started with ERA5, which came to the last few years, being a training set for data-driven weather forecasting and much more. And this is really important. It's really fastly growing, but also this also makes reanalysis even more important. So reanalysis was, and NWP was kind of separate, but now reanalysis becomes an extremely important component for doing the best NWP. Okay, so what is CFRES? So, because part of the activities are for ERA5, ERA5 is produced with CFRES funding. So it's part of Copernicus, which is the Earth observation program of the European Commission, and ECMWF operates the Copernicus Climate Change Service and Copernicus Atmospheric Monitoring Service on behalf of the European Commission. And one central part of our services is this climate data store, where we provide a lot of data sets, climate data over our past, our present, and also our possible futures. Reanalysis is an essential part of that. Just to show you that we introduced a new climate data store, and a lot of the things that were, everything what was there in the past is still there. But what we also have is interactive web applications like Climate Pulse and Atlas. Is really nice. And what we already have, but is important to mention, is that one of the good things about the climate data store is that we also provide quality assurance reports on our data sets that we make available. Shunxi knows everything about that. And we have a forum where users can interact with each other, and we also have user support when people really need dedicated input feedback from us. Okay, so here I'm going to a little bit explain how ERA5 works, the data assimilation system, because I need that later to explain what is new in ERA6. So we have this system of outer loops where we, where we do 40 VAR. We have 40 VAR for the atmosphere, where we try to find the best initial condition based on a short forecast first guess that fit the observations best, but also taking account of some trust in the first guess, which is represented with this B matrix. And we do it in an incremental way to deal with non-linearity. So there's a number of outer loops of doing that. And in between we have 40 VAR, where we only assimilate atmospheric observations. And the result is an analysis of upper air variables plus a number of service parameters. But then we also have an ocean wave analysis, where we assimilate altimeter wave height using optimal interpolation, and it produces a 2D wave spectrum and a large set of integrated parameters. And then there is a land data assimilation system, which is kind of outside the outer loop, so it's weakly coupled. And that is a sum of univariate OIs for 2 meter temperature, 2 meter relative humidity, soil and snow temperature, and we have also an SEKF for soil moisture. And that produces a number of surface and lake parameters. And then we have SST and CI, so because we have to the atmosphere, we have to force it, we have to have constraint of the SST and CIs. And that's basically directly provided by an external source. And we do some analysis step, that's basically some very kind of fine-tuning between SST and CIs to make sure that we have SST, what the SST is on the eyes, and when we have SST is too high, we don't have CIs and things like that. Okay, and also note that quite a few parameters are not taken from the analysis service, but are not taken from the analysis itself, but from these short forecasts, which are in between these, these analyses. And there are alternatives, and for precipitation, there is a poster on Wednesday on that. So please come to have a look at that if you want to know more about that. Good, so then we also have an ensemble data assimilation system, where the goal is to estimate a flow-dependent B matrix. But for ERA5, so you need that for the machinery of running the data assimilation system. But for ERA5, we also use that to give that to users as a guidance of the accuracy of the reanalysis. That's something which we didn't really have in ERA interim, and that's really a nice, one of the new features of ERA5. So we have 10 DA systems, exactly the same as I showed in the previous slide, but at half resolution, and we perturb observations, including the SST and the CIs, according to their uncertainties, and we also perturb the model in the short forecasts, linking these analyses. And there you get this spread, and from that you determine the flow-dependent B matrix. But it doesn't stop there, because besides this flow-dependent part of B, the B matrix also depends on a climatological B, which is more represents the maturity of the observing system as a whole. Where you have more observations, then your first guess is supposed to be more accurate. Therefore, you have to give more weight to it compared to the observations which you then assimilate in a data assimilation cycle. There is some alpha factor which we can play with to have the relative strength between the two. So both are important, and actually this appears to be very important for ERA5 because this is all based on NWP. This works very well. This is an example where you do reanalysis, you always have to do a bit difficult, that maybe NWP not always works out of the box. And this was a classic example of that. So we found that if we run the operational climatological B, which was determined for an observing system for a recent time, 2016 at the time, that when you go back to 1979, we didn't get very good results. So thinking, at the end of the day, we figured out, okay, we have to adapt this climatological B because the observing system has changed so much by 3 orders of magnitude that we have to do something about that. And we did that. We determined these B matrix, climatological B matrix for an older periods for exactly the same way as they do in NWT now for the methodology for a more recent period. And we found that, of course, if you go from more towards historical periods, that your B matrix they become less tight. And also the length scales become longer because you have to make larger scale corrections in order, because you have less observations, and the more observations you have, the smaller scales you typically only want to assimilate. So we were very happy, and that all worked. But then we found that, and we only changed the climate RQB when we have big changes in the observing system. So one of them is when you go from the TOFs satellites to 8 TOFs, which is around 1998 or 1999. And we changed the B matrix, the climate RQB in the year 2000. That we then compare it with the Radisson data, first gas departures. You get the red curve there, and we see a jump there between 2000 and 2006. That's not really what we wanted. So what's going on here? So what now appears is that we have model bias. Again, how important that is. We have a systematic cold bias in the ERA5 system in the model, and therefore you need anchors. You need anchor observations that are not bias corrections, because a lot of the observations we use variational bias control. So basically, they just adapt to what the model, they can adapt to the model. You can alias model bias into the observation bias. So we really need anchors, and we only had Radisson data then. And when you change the B matrix, the Radisson data is relatively sparse, and then they don't have enough weight anymore with this new B matrix, which gives higher weight and all the smaller correlation lengths, and then the Radisson, they can't cope, and whoop, that jumps your relative departure with Radisson data. And only when we have a lot of anchors, which in 2006 with the radial occultation, you go back to normal. So what we did is we run ERA5-1, which is basically a continuation of using the same B matrix in the TOFs period, and that works. So basically, from theoretical point of view, when everything is unbiased in a data simulation system, we should have gone for ERA5, but in practice, where you also have systematic biases, that actually is not the maturity of the observing system itself, which is important for those biases, is the maturity of the observing system, of the anchoring observations, what is important, and that didn't change in 2000. Okay, so the observing system has changed a lot, as already said also by Shinya. So just to give an example, in ERA5 in 1940, we only used 70,000 observations per day, and in 2021 there was 26 million, so that's more than 3 orders of magnitude. Okay. We had no satellites before the 70s. Before 1945, we have no upper air data, so that the cold bias can pop up that we have in a model. That then compromised from 1940 to 1945 the mean temperature in the stratosphere. Okay, now about, there were already questions about how can you diagnose the accuracy of reanalysis and why you have less observations. Well, this is exactly this ensemble spread which we can use there. And this is a product that people have, So, and especially how that compares to climatology. So here I show you, this is an example for surface pressure. You can do it for any parameter, because we have that in our data sets, in the ERA5 and the climate data store. So I look here at the natural variability of surface pressure, where I take out the daily and the seasonal cycle. You see where you have the largest variation. So when you have an ensemble spread which is much smaller than this, then you say, okay, you can trust the synoptic accuracy of ERA5. So when you do that for the 1940s, you see you're fine on the northern hemisphere. On the southern hemisphere, last part of the southern hemisphere, you're absolutely not fine. You don't have many observations, so basically you have no synoptic accuracy there. It doesn't mean that ERA5 is not valuable there, because still the model climatology can still give a good representation in theory about the low frequency variability. It's just for those applications where you also need synoptic variability, you can't use it. But that's within this data set, within this partial statistics. And so in this standard deviation in the ensemble spread. Now, when you go further in time, closer to nearer time, here, the ultimate here, the last decade, and everything is much better. And there's still a little spot there over, we talked about it already, Central Africa. That you can actually see that over Central Africa, there we have less observations, and that's why the accuracy of ERA5 is lower. So we're using the ensemble spread you can get a very good indication about the quality of your reanalysis. Okay, I talked too much about ERA5 already. So other reanalysis activities at ECMWF. So ECMWF has a long experience of reanalysis. So ERA5 is the combination of a number of atmospheric reanalysis. Then we have dedicated ocean reanalysis. So Hao Zhu will give a presentation later this week about the ERA6. Then we have a centennial reanalysis with sparse input, and also more experimental reanalysis where we have outer loop coupling with the ocean, fully coupling, two-way coupling with the ocean applied. And there's different components here: land, atmosphere, ocean, composition, wave, and ice. Those are reanalysis that the domains where ECMWF has experience with in running reanalysis. But they're not all, of course, coupled, and as I show here. And then we have enhanced land reanalysis, and finally also atmospheric composition. So what's next? So ERA6, which is being produced, that use at the moment forcing from ERA5, and when it goes to the nearer time, it will use forcing from NWP, and it will also be used in our NWP system. And ERA6 will use the input from ERA6. So how does that work? So I already showed you the diagram for ERA5. Now the time goes from right to left in the DA window. So the difference in ERA6 is now that in these outer loops we have also the ocean and the ice model coupled with NEMO 4 and sea ice cube. Although we don't assimilate in the simulation system, we still only have 40 VAR, and we have the land data simulation, so we don't assimilate atmospheric observations, but the information from the ocean state comes from ERA6. So with every analysis cycle, we impose that at the initial state of the start of the simulation window, and then we do this outer loop coupling, and everything is in the outer loops, and also the short forecast is fully coupled, and then it can have of course the ocean state changes in a fully coupled way, and also atmospheric observations will have an influence of the ocean state later in the assimilation window, not at the start but later. So that's how we do it. We'll do it in ERA6. As I already said, Hao will give a talk about ERA6. And on looking at the impact and of those data sets, and also selection of data sets for ERA6, Alison Kopp has a presentation on that tomorrow. Okay, so you get a positive impact where you expect, so near the surface, ocean surface, and also particularly improved ocean wave forecast, not only because the ocean wave generation is now taking care of the relative stress, which is relative between the wind and the current. We have also currents now, but also we have current refraction. So when you have swell that goes over the tropics, travels thousands of miles, it gets deflected by currents which we didn't have previously. The way they compare with the partial statistics, with surface observations, here this plot on the left means better compared to a control. There's several experiments here. Control is when we don't have any coupling. That you see exactly the positive impact where you expect. Okay, towards our ERA6, I already mentioned that one of the big things will be this coupling with the one-way coupling with ERA6. But in general, ERA6 will benefit from an additional 8 years of R&D at ECMWF, plus also the improved compute capacity. So we will go to much higher resolution, 14 kilometers for all components. So the waves used to be 40 kilometers, will also be 14 kilometers, and that should improve the estimate of extreme weather. Then the certainty estimate will be at 28 kilometers. Then science, and is selected because during these 8 years a lot of things have happened and have improved. So the first bullet point I already explained. Then we will have improved realism, like introduction of an urban tile, which we also want to evolve over time. Then improved treatment of systematic model errors, very important. And Bill Bell has a talk about that, or how we we use a neural network changed on weak constraint 45. Then we evolve CO2 in the assimilation of satellite radiances, which at the moment when we don't do that, then the height of the weather, when the windows peak, they have a bias and they have to correct for that. And when you adapt CO2, that will be more ideal. And also evolution of CH4, for methane, for improve lower stratospheric humidity. Then we have improved greenhouse gases and aerosol forcing, which will also help energy budgets. We have a new ozone model called HLO, and now it's also prognostic with radiation. So for ERA5, the ozone, although we have prognostic ozone in ERA5, in the radiation code we use diagnostic ozone. Now they will be fully, consistent. Then we take into account snow and ice, and we reduce, which we didn't have before. In general, we reduce snow depth bias and inconsistency in snow. And especially want to thank Kenta Ochi, who has been working at ECMWF for a few years and worked particularly on this. Then we will have better forcing for large lakes, where we made some errors in ERA5, and we will resolve several other known issues of ERA5. Then we will ingest the best observations. So we do a lot of satellite and in-situ reprocessing and data rescue together with our contractors. And Paul will have a talk about it tomorrow. And we now also assimilate 2-meter temperature observations in 4D VAR, in addition to also in the land data simulation. Then another thing which is really important for reanalysis are the products, because our users want much more than a standard output of a standard experiment what we run. So we spent a lot of time on that, and it's based on user requirements. So ERA5 was hourly, there was a user requirement. ERA6 will be the same. We will add some new parameters like 2-meter relative humidity, because now you have to calculate it from ERA5 parameters, which is a pain. But we also have things like clear air turbulence. We will have height levels, that makes it particularly more suitable for non-technical users. And we want to add daily, in addition to monthly pre-calculation statistics. One example of the impact of reprocessed data sets produced by EUMETSAT, they're working with us as a contractor on this, is the assimilation of, we have now access to reprocessed Hertz radiances, because in ERA5 it's a mix and match, and now everything has been done much more properly. So here are 2 periods where we have done some tests to see whether it works, and I will show you some results from 1991. There you see on the left, you see the impact. So we do always these kind of experiments. It's for 6 months. The standard without the old way and then the new way. And blue means an improvement in forecast scale. And that's indeed what we see. It's mostly blue. And also when you look at the departure statistics on the bottom right, when you go to the left, it's typically better than a control. So that works out all very well. Okay, some general preliminary results of ERA6. So the horizontal grid, so we have much higher resolution, which you can particularly see over orography, like the Alps. Then, small scale variability, so how much and that's the nice thing is to look at energy spectra. I show here results of TCO 639 and TCO 709, which are 2 resolutions that we tested for ERA6, and we went for TCO 709, which is 14 kilometers. And you see much more small scale variability compared to ERA5. This is good. Then where you do verification of tropical cyclones, this is actually only a 3-month experiment where we was not in the hurricane season, but we sense here in other areas tropical cyclones. But in general, the impact of ERA6 test runs are very good, particularly also the pressure-wind relationship is much more like that is from observations like the IBTRAX data set. Then departure statistics. These are first guess departures. So where you simulate data, the analysis departures are typically quite decent because you simulate them. But then 12 hours later, or 3 to 15 hours later, these departure statistics, they can bounce back when you have model biases. And that is a bad sign. So systematic model bias is one of the prime enemies of reanalysis. And that's really, we need to get that under control and to eliminate that. That's really, at that point, that's really a good, we're getting there, but of course we're not getting there tomorrow, but we're getting there slowly. So, but surely. So we have much smaller departure statistics in ERA6, which is a very good sign. Then the lakes, we really now compared with buoy data to see which data sets that we had, external data sets, are the best ones to use as forcing of our flake model. And Ostia reprocessed was the best data set. It's not the same story for the ocean, though, but that will be, Alison has a talk about that later, and a poster. And then the ocean currents. So now we have, we have them in ERA6, and they're also evolving hourly. Okay. So, production plan. So this is preliminary. We, how long do you have? 1 minute?
We already finished in the minutes, but we have less minutes for questions.
Okay, good. So production plan. We start early next year, and we will have start with 2 streams, then we have another 2 streams in such a way that at some point we always have 4 streams running at the same time, and then we will finish by mid and the end 2028. Okay, beyond ERA6, so we'll continue to build on synergies with R&D at ECMWF. So there are 3 components there. One is to enhance the consistency of individual components, like unifying the land data simulation system. Then the second is to improve the coupling between the components, and thirdly, to enhance the exploitation of service observation, of interface observations that have foot in more than one component. And an example of that is the unified land data simulation development that we're currently performed in the Ceres project. And we have a poster on that tomorrow. Okay, sorry for taking too much time. Final remarks. We have nearly 85 years of data. It's maintained in near real time. So there's a poster by Luca about that. So if you want more about how we do that, we are preparing for ERA6. We have a long experience with reanalysis. We are continuing to be aligned with synergies with RD at ECMWF for future reanalysis, and observations are really key. And we work together with our contractors. Here I only mentioned EUMETSAT and Spatial for the satellite contracts, but we also have contracts with Maynooth University, CNR, IMA, and KNMI University of Vienna on data rescue and reprocessing of in situ observations. Thank you very much.